Moments of inertia, type 2, compound pendulum, periodic time. So we're going to look at page 247 in our textbooks, and we're looking at the example 14.5, where we have a rod and a disc attached as a compound pendulum system, and it's free to rotate around the axis through x. So if I mark x in red, that's our axis point. So we're told that the rod has a mass of m and a length of 6L. So if I mark in the midpoint on the rod at C, that means we have 3L to X and then 3L to Y. And we know that the disc has a mass of 3m and a radius of L. So there's L and L. And the centre of the disc, we just call it C here, is on the same line that is matching the rod. So in other words, the centre of the disc and the rod and X and the point Y all lie in the same straight line. We're told that the pendulum performs small oscillations about a horizontal axis through X, which is perpendicular to the plane, and we're asked to find the periodic time and then also find the length of an equivalent simple pendulum. So the first thing we always have to do in these questions for periodic time is, like always, find our moment of inertia for the system. So if we're going to find I for the system, we'll start with the rod first. So our moment of inertia for our rod, we know, is on page 53. And obviously, if we were going through the centre, it would be a third ml squared. But because we're looking for it through the axis of x, that means that we're actually taking the moment of inertia about the axis at one end perpendicular to the rod. So we say the moment of inertia for the rod is going to be 4 over 3 ml squared. So if we sub in our mass and our L, and I say it's through the axis x, the mass of the rod is m, and from the centre to the end is 3L. So we put in 3L for L. Make sure you're squaring that. So that gives us 9L squared times 4 over 3m, which is 12 ml squared. So we have the moment of inertia for the rod. We now need to find it for the disc and then for the system. Okay, so if we look at the disc, first thing we see is on the top of page 53 here, we have the uniform disc, which is a half mr squared. And that's through its centre C. So the moment of inertia through C is a half mr squared. But I want it through the axis X. So again, if I just draw to the side here, if I mark in X, if I was to put my pencil on X and I put my pencil on C, we can see that the axis X is parallel to the axis C, which means we have to use the parallel axis theorem, which is the second last here from the bottom. So it's going to be the moment of inertia through C plus md squared. That's our parallel axis theorem. So I'm going to do this all in one go. You can, of course, work them out separately. So I'm going to sub in, but we have to be careful here now. Moment of inertia through C is a half m. The mass of the disc is 3m. The radius of the disc is L. And then plus m, so that's 3m. And the distance. So D is from C all the way down to X. So if I mark that in on my diagram, that's going to be 6L plus L, which is 7L, and 7L squared. So therefore we get 3ml squared over 2 plus 49 times 3, which is 147 ml squared. So adding those two together, the moment of inertia of the disc through X is 297 over 2 ml squared. Okay, so now we have the moment of inertia of the disc through X and we have the rod through X. Then all we have to do is write down the moment of inertia of the system. So for the system, it's the two together. So it's the rod through the axis X plus the disc through the axis X. So therefore, adding those two together, is 12 ml squared plus 297 over 2 ml squared. So the moment of inertia through x for the system is 321 over 2 ml squared. Okay, so now we have the moment of inertia of the system. We're ready to look at how are we going to find our periodic time. So of course the periodic time for our compound pendulum is given by t is equal to 2 pi times the square root of I over mgh. And this can be found on page 54 in our table. So we have the simple pendulum and we have the compound pendulum. So we're looking at the compound pendulum here. So we've found I, so we know what the mass of the system is going to be, we're given that. So we also need to find h next. So this is our step 2, to find h. So to find h is basically where all of the mass of the system appears to be acting to the axis of rotation, which we know is x. So h is where all of the mass of the system is working, but we don't really know where that is. So that's why we have to work h out. So we know that the mass of the disc is 3m and the mass of the rod is m. So our weight of the system, in other words the force, is the disc plus the rod, which is 4m times g. So remember, weight is mass times gravity. Okay, so that's for the system. And then we have the two parts separately. So we have the rod and we have the disc. So we have the weight of the rod will act through C, which is a distance of 3L to the axis point. And therefore we have our weight is mass times gravity. And then we have the disc, which is a mass of 3m. So therefore the weight is 3mg. And its distance is L plus 3L, which is, of course, 7L. Okay, so the distance from the centre of gravity of the rod to the axis point is 3L. The distance from the centre of gravity of the disc to the axis point is 7L. And the distance from the centre of gravity of the whole system is h, which is what we're going to try and find. So therefore, basically what we know is that the sum of the moments must equal the moment of the sum. In other words, the moment of the system. So in other words, if I get our moment, remember moment is force multiplied by perpendicular distance. We know that from physics. So the sum of the moments, we do that one first. Well, it's going to be the force by perpendicular distance. So it's the disc, and the force is mg by the perpendicular distance is 3L, plus the disc, which has a force of 3mg by the perpendicular distance, which is 7L, and that must equal the moment of the system. And therefore that's going to be force, which is the weight, by the perpendicular distance, which we don't know. We're trying to find what h is. So all I need to do now is simplify the left-hand side. So I get 3mgl plus 21mgl is equal to 4mgh. And we can add the left, so that's 24mgl is equal to 4mgh. And of course then we can see that there's an m on the left and the right, a g on the left and the right, which means then that h must be equal to 6L. So in this case that actually means that all of the weight is acting at this point here, because that's 6L. That's where it's really acting for the system. Okay, so now we have H and we know I. We can go back to our formula here at the top of the page for a period of time, and all we have to do now is sub in. So we say T is equal to 2 pi over the square root of I, and we said I was 321 ml squared divided by 2. Just make this square root sign bigger. So that's I, and then that's divided by the total mass of the system, which was 4m, times gravity, times h. And we've just worked out h to be 6L. So let's simplify this. So we have T is equal to 2 pi. And I'll just drop down that 2 there. So we have 2 times 4mg times 6L. And therefore that gives us 321 ml squared. And on the bottom then we have 48. So 8 times 6 is 48 mgl. And m will go into m once, L will go into L squared, L times. And that leaves us with the periodic time for the compound pendulum to be 2 pi times the square root of 107L over 16G. Okay, so part 2 then says we'll find the equivalent length if it was a simple pendulum. So our simple pendulum is if we have an inextensible string that's negligible in mass, and we have a tiny dense sphere attached to the string, and it's free to swing, as we did last year in physics when we were doing our simple harmonic motion and our simple pendulum. So what we say is the periodic time for a simple pendulum is L over G. So if we go back to our tables there again, bottom of page 54, this time we see our simple pendulum just above the compound pendulum. And to distinguish between the L that we've used in our compound pendulum and L for the simple pendulum, we're just going to change this L to a capital L so that we don't get confused, okay? So in your tables you see it as a small L, but for the purpose of these questions it's always better to distinguish between them. So we'll say capital L over G. All right, so equivalent means we equate. So we're going to equate our simple pendulum formula to the value we got for our compound pendulum in this particular case. And you can see we have a 2 pi on both sides, so we divide across by our 2 pi, which leaves us with the square root of L over G is equal to the square root of 107L over 16G. If I square both sides, I'll get rid of the square root sign. And therefore I have L over G equals 107L over 16G. And I can multiply both sides across by G. And therefore the equivalent length of a simple pendulum to give the same periodic time in its swings would be 107 over 16 times L. So for a second one here, we're doing page 250, example 14.6. And again, what we want to do is find our periodic time for small oscillations around the axis. And the axis this time that we're given is through a point X from the midpoint. So this Y value here is our axis of rotation. But the second part that's different to the previous example is that we have to go one step further and we have to find the value of X for which this periodic time is a minimum. So if we're looking for a minimum, we know from maths that we have to differentiate. So same as before, we're going to start with step 1, which is finding the moment of inertia of the rod. So we have a rod of mass m, length 2L, has a point mass m attached to its midpoint. So this is a nice question because the point mass is actually attached to its midpoint. So that means that the mass of the rod will act through the centre of gravity, and then the point mass is acting through the centre of gravity of the rod, and therefore the mass of the system is all in the centre of the rod. So therefore we don't need to work out h this time. We know that h is actually going to be this distance here from y to the centre. In other words, h is going to be x. So let's get the moment of inertia first of all. Okay, so if we look at the point mass, well, the moment of inertia for a point mass is md squared, and therefore I through y is the mass of the point mass, which is m, and the distance from the point mass to the axis of rotation is x. So therefore that's going to be mx squared for the point mass. If we do the same now for the rod, well, for the rod, the moment of inertia is going to be through its centre, which is a third ml squared. I can't take it from the end because y isn't at the end of the rod, so we're going to have to go through the centre. The mass of the rod is m, and it's going to be, the rod length we're told is 2l, so therefore from the centre to the end of the rod is l. So it's literally just going to be a third ml squared. But of course, if I look at C and I look at Y, if I was to put my pencil on Y and my pencil at C, I can see that Y is parallel to C, which means that if I'm getting the moment of inertia of the rod through Y, I'm going to have to use the parallel axis theorem. As we saw in the previous question, it was on page 53. Okay, so subbing in, we have a third ml squared plus the mass of the rod is m, and the distance from the centre to y is x. And obviously I can't add those two together, so it's just a third ml squared plus mx squared. So therefore for the system, we add the point mass and the rod together. So the moment of inertia of the system through y is going to be a third ml squared plus mx squared plus mx squared, which gives us a third ml squared plus 2mx squared. Okay, so now we're ready to get our periodic time. So we know our periodic time is 2 pi times the square root of I over mgh for our compound pendulum. And therefore if I sub in my moment of inertia that we just found, it was a third ml squared plus 2mx squared, and that's divided by the mass of the system, which we know is 2m, times g, and times h, which we said is x. So I'm just going to simplify that and tidy it up. So I'm going to multiply the top and the bottom there by 3 just to get rid of the fraction. So if I multiply the top by 3, I get ml squared plus 6mx squared. And if I multiply the bottom by 3, I get 6mgx. Now I can see obviously that I can divide the top there by m. So therefore I get t is equal to 2 pi times the square root of l squared plus 6x squared over 6gx. Now if I go back to the question though, it didn't want me to find t, it wanted me to find t squared. Okay, so that means I'm going to square both sides. So if I square the left, I get t squared. If I square the right, I get 4 pi squared times l squared plus 6x squared over 6gx. And again, just going back to the question, it wants me to take out the 3g also. So if I take out the 6g That leaves me with L squared plus 6x squared over 6x. And then, of course, I can divide the top and the bottom there by 2, which is exactly what we wanted to get. So t squared is equal to 2 pi squared over 3g, which is clearly just a constant, because pi is a constant, 2 is a constant, 3 is a constant, and g, gravity, is also a constant. So now we have our periodic time squared. Okay, so that's the first part done. The second part then is to get the minimum. So to get a minimum, we know that we have to find dt dx, but we have t squared, which is obviously going to be even smaller again, and therefore finding t squared is the same as finding dt dx. So we're going to find the rate of change of dt squared dx, and we're going to let that equal to 0. And solve for x. Okay, so if we look at our function, we have t squared is, we say there, 2 pi squared over 3g times L squared plus 6x squared over 6x, right? So if I'm going to differentiate this function, I clearly see that I have an x on the top and an x on the bottom, so it has to be the quotient rule. So our quotient rule is going to be do I dx is equal to v times du dx minus u times dv dx all over v squared. So rather than writing do I dx, we're going to be saying dt squared dx is equal to, and that 2 pi squared 3g is just a constant, so we're just taking that out. So we're just integrating this bracket L squared plus 6x squared over 6x. So let's do our rough work over here to the side. So u is the top, so L squared plus 6x. If I'm differentiating u with respect to x, well, L squared is a constant, so it goes to 0. And if I differentiate 6x, I get 6. V is equal to 6x, so if I differentiate 6x with respect to x, I get 6. So we have v times du dx minus u times dv dx all over v squared. So if we simplify the top line there, sorry, I just realized that's L squared plus 6x squared. So that should actually be a 12x. Sorry. So that's v times du dx. So v times du dx. So 6x times 12x minus L squared plus 6x squared times 6 over 6x squared. Yeah. Okay, grand, sorry. So constant, again, just keep it outside till the end. Multiplying out your brackets, so 6 times 12x is 72x squared. 6 times L squared is minus 6L squared, and 6 times 6x squared is minus 36x squared, and 6x to be squared is 36x squared. And then we can simplify that top line. So 72x squared minus 36x squared is 36x squared minus 6L squared all over 36x squared. And I can divide the top and the bottom there by 6. Which gives me 6x squared minus L squared over 6x squared. Okay, so we're going to let that equal to 0. So this is our derivative. Remember, it's just our first derivative. And then we let the first derivative equal to 0. To solve for x, so that's 2 pi squared over 3g times 6x squared minus L squared over 6x squared. So we're letting that equal to 0. So if I divide across there by the constant, 0 divided by a constant is 0. Multiply both sides across by 6x squared, which gives me 0. 6x squared equals L squared. Therefore, x squared equals L squared over 6. Therefore, x must equal the square root. And obviously, I can't have a negative distance, so I wouldn't be using the plus or minus answer here. I will only be taking the absolute value. And therefore, x is L over root x. So we say can't have negative distance. Okay, so we now want to show that this is definitely a minimum. So if we do the second derivative test, to show it's a min, so if you're asked to prove it's a minimum, then we would get the second derivative. So if I go back, my first derivative we said was 2 pi squared 3g. Let me write that out again, sorry. So we had 2 pi squared over 3g, 6x squared minus L squared all over 6x squared. Okay, so again, if I'm differentiating, we'll have u and v. So u is going to be equal to 6x squared minus L squared. So du dx will equal 12x. And v is equal to 6x squared. So dv dx is equal to 12x. Okay, so if we get our second derivative, again, constant, just keep it out. So it's v times du dx minus u times dv dx all over v squared and therefore on the top line we have 72x cubed minus 72x cubed minus is plus 12xl squared all over 36x to the power of 4. And we can see 72 is gone. So that leaves us with our second derivative is 2 pi squared over 3g times 12xl squared over 36x to the power of 4. So if we test our x value, so when x is L over the square root of 6, then if I sub in, actually I can simplify that x will go into that. So let me just, that's 2 pi squared over 3g times, and 12 goes into 36, so I can actually simplify that nicely down to L squared over 3x cubed. So if L is subbed into that, we're clearly going to get a positive number because 2 pi squared over 3g is positive. L squared is a constant, and then it's 3 times L over root 6 cubed, which is equal to 2 pi squared over 3g times L squared over, which is root 6L cubed over 12. And then that simplifies down to 8 pi squared over root 6g L, which is greater than 0, hence minimum at x equals L over root 6. Okay, so again, you always do the second derivative test if you're asked to prove that it's a max or a min, or if there's two and we don't know which is which. But in this case, there was only one value, and therefore it had to be a minimum. and it just says find the value for x for when the time is a minimum. So on the exam questions, you're going to do 1988 and 1992. And when you're doing 1992, look down on P as if you're literally looking in, so you're looking in a vertically downwards. So like you're looking down on this point here. So P and R would be in the same position, and then you'd have Q and S out here. Okay, so that's your hint.